Hi everyone, welcome back. In this video, we are going to look at how we can use our own custom data set where you have images and masks. How can we use those to train your own custom segment anything model? Of course, I'm going to talk about what it is, what the model is, and then we'll jump into the code part. And I definitely recommend watching my last two tutorials on the topic of Detectron 2 for instance segmentation. I am a super big fan of that approach, so please go ahead and watch those if you haven't already done so. And you can search for videos number 329 and 330 if you're looking for those Detectron tutorials. And for any future ones, if you want to be notified, I recommend hitting the subscribe button right now. And while you're there, if you're feeling extra generous, try to find the little thanks button. Okay, now getting back to the topic, let's start by looking at or understanding what this SAM is all about. And of course, I'm doing this video because this has been a buzzword recently, right? I mean, it can detect anything. That's what the segment anything model stands for. Now, it's an image segmentation model, and that's developed by Meta AI or Facebook AI, if you want to call that. And it has been trained on multiple segmentation masks, over 11 billion segmentation masks. And these masks are coming from millions of images. So millions of images with multiple segmentation masks, well, 11 billion segmentation masks. That's why it's kind of segment anything model. Now it's designed to take, in addition to these images, like human prompts. You have to supply a prompt, and that prompt can be in the form of a points. You can say, hey, here are the points of interest. Go ahead and find the objects. It can be bounding box. You can say, hey, I want to draw a bounding box, or it can even be a text input that will be embedded obviously into some sort of an embedding and provided as an input. But this is at a high level what segment anything model does. And why do people care about it? What are some of the key features? It's ability to zero-shot generalize. That means it can be used to segment objects that it never ever saw before. Okay, then you may ask the question, why do we need to custom train it on our own data sets? We'll see reasons why we should do that in a minute, but by actually doing a practical, like let's upload an image that we plan on actually using as our training image later on, and then see how the segment anything model does to get a feel for what it is. And then let's go ahead and train the model. Okay, I'm assuming this is going to be a long video, but I appreciate your patience. And the prompts, you can provide the prompts in a flexible way. That's why people like this, because like I already mentioned, it can be a bunch of points, it can be a bounding box, or it can be text descriptions. And also it's very fast, so it helps in real-time applications like autonomous driving, for example. If you want to detect things in real time, this can be a pretty good algorithm. And of course, ambiguity awareness, which means you have objects that are kind of overlapping, and it's like, yeah, I know there is another object underneath this object, so it kind of in those situations. Although Detectron also does a pretty good job when it comes to instance segmentation and overlapping objects. Now, if you ask me the question of, okay, given Detectron and segment anything, which one would you use? I always go back to Detectron because that is, at least in my point of view, that's more appropriate for scientific image analysis applications. Although I should admit my limited, practical experience with segment anything model. So based on that bias, I should say I naturally lean towards Detectron. It has been more reliable given on a couple of data sets that I worked with, at least. Okay, between these two, SAM and Detectron 2. Now, I'm not saying stop watching this, of course. Maybe you'll find that this approach is more appropriate for your data set and you get to test it on your own data. Okay, let's jump into how or continue the discussion of how it works. This is the paper. I encourage reading this paper. I'll leave the link as part of the description, but the way it works is if you look at the left hand side, right? I mean, what is going as input into your model? Well, it's one of these segmentation prompts. It can be individual points, it can be a box, it can be like your outline around the object, or it can be just a text. Hey, cat with ears, right? And an actual image goes in and the model takes that input and then it gives you an output. In this case, cat with ears. And the input that actually goes is two inputs like we just saw here, right? So there is a prompt and there is an image. And they both go into this lightweight mask decoder, and it generates this valid mask. Now, we'll get into one level deeper. I'm not going to go too much deep, but one level deeper. So you have an input, in this case, a scissors, right? So, and that image gets encoded into a image encoder. So, you have an image embedding right there. So, which is nothing but a vector, right? So you have an image right here. In fact, I probably put this in the form of text. So it first encodes the image into a high dimensional vector representation. So now you have a vector that represents this image. In addition to this, we know that we have to supply prompts, right? It can be points, it can be a bounding box, it can be text, but it doesn't matter. That gets converted into another encoded vector. So the prompt is another vector. Now both of these actually go in. They're combined and passed into this mask decoder, which outputs this mask, and it gives you a score. Hey, this is a scissors, and what is the score? This is like, I don't know, part of it, what is the score, and so on. So now the image encoder, what is it? It's nothing but a vision transformer. It's a VITH. In fact, when we train our own, we are going to download this model. And it's a large language model that has been pre-trained on a lot of images, like we already talked about. Now, the question is, wait a minute, we're talking about images and you're mentioning about language model. Yes, it can be. A language model can be used for image analysis tasks, but first we have to encode the image into a text representation. That's exactly what these guys do here. And then the prompt encoder is basically a simple text encoder that converts your input prompt. It can be a text, it can be points, like I already mentioned. It converts that into a vector representation. And the mask decoder is basically a transformer model that predicts the object mask based on these input embeddings. Now, how do we fine tune it? And when we say fine tune, we're not changing weights of any of these. We are just adjusting the weights in this mask decoder part. So we are fine tuning the mask decoder. And how do we, what do we need to actually fine tune it? Well, obviously you need to be ready with your own custom images and corresponding masks. Right? The masks again can be in whatever format, but what I'm going to walk you through today is actual images and actual masks that you would have typically, normally. I'm not going to use some theoretical data set or some data set that you download from somewhere, via the code. We are going to physically download a data set from a source that comes with images and masks, and we're going to use that and train our own model. So this is a complete walkthrough that you should be able to reproduce. And if not already available, bounding boxes for each object, because we need some prompt, right? We need either points or box or text. So we'll generate bounding box, which should be pretty straightforward. Again, we'll look at this in the code. And basically, this is what I'm talking about. We have an image and corresponding mask, where it shows where, in this example, where the mitochondria is. And then we basically just binarize this image and say, hey, in this image, just put a box around this object. If you don't have already, right? In this case, we don't have it. That's what we are trying to do here. Now, why is it so important to have the prompt? Obviously, because prompt is also part of the inputs. But if you actually look at the output with and without the prompts on the top, you can see how the probability map is, where I haven't supplied any prompts, but down here I actually supplied a random grid of points. I'm like, hey, do 5 by 5 grid or 10 by 10 grid. And this is how the probability output looks like. Okay, I think this is enough background information. I'm sure most of you are eager to jump into the code, but before jumping into the code, I want you to have another look at Segment Anything model on their webpage. Okay, so when you go to segment-anything.com, this is what you're going to see, and it kind of summarizes exactly what it is designed to do. There you go, prompt with interactive points, or you can just generate a grid of points, or you can do other stuff. Now, let's do that firsthand. So let's go to demo. It says something, agree to segment anything terms and conditions. Of course, I want to do that. You can use one of their pre-existing images here, or you can actually upload an image yourself. So let's go ahead and upload an image. And by the way, I should actually start with showing you the type of data set we are going to work with. And that data set can be downloaded from here. I'll leave the link as part of the description, or just Google search for mitochondria dataset EPFL. So I absolutely love this data set. It comes with a TIFF stack, TIFF. I hope you know what TIFF images are. It's a TIFF stack of 165 slices, 165 images, each of that specific size. So we'll look at this in a second. So I downloaded the training data set here. You can also download the testing if you want. So training data set, it comes with a 165 images and corresponding masks. And these masks are just binary. And I just downloaded them, and let me open those so we can have a quick look at this image. Okay, so here it is, and now you can see these are images, which is basically a TIFF stack. And what do we mean by TIFF stack? It's just a stack of images. And this is, in fact, a 3D volume that's stored as a TIFF stack, and this is corresponding through mask right here. And the mask is binary. You can see when I put my mouse in the background here, at the footer of this image J, you should see a value of 0. When I move it to this bright region, it's 255. So it's a binary image, 0, 255, that's it. Okay, now this is enough information. Let's go back to where we were. What we were discussing was the segment anything model. So I took one of those images, the first image basically of this 165 images, and now let's go ahead and upload it. And now it got uploaded, and it's extracting embeddings. Now you can see how it's not bad. I mean, I put my mouse right there. It's actually showing the object. I put my mouse right here. I mean, it's not accurate. This is why we need to train it, right? So this is, I put my mouse. This is perfect. That is perfect. In fact, I can actually add a box. So let's go ahead and add a box. Let's do that around this object and see if it picks it correctly. Not really, right? I mean, this is the mitochondria, but it's actually picking the regions surrounding. And I believe you can actually draw a box to remove certain area. So you can kind of say, this is my positive, that's your negative. But this is exactly what we do when we train it. You know, why we do that for every object. In fact, if I draw the same here, I'm not sure. Let's see. That's actually, I mean, if I put a smaller bounding box, it probably does a good job. Anyway, so that is bounding box as an input. What if I just put everything? Everything is nothing but it puts a grid, as you can see, on the image. So it's actually applying that as a prompt. It's applying that as a prompt. And again, this looks like it's doing an amazing job, but not for scientific images. This is not accurate for scientific images, right? I mean, you don't want to take some of the background pixels. You don't want to include this background around these two mitochondria and wrongly call that mitochondria, right? So that's not mitochondria. That's just some shape up there. This is, of course, and a whole bunch of objects are missed. Look at these two. These are missed. That is missed. That is missed. And this one is not picked up. So there's a lot of objects. So upon first look, because it is colorful, we think that, wow, this is doing an amazing job. But there is a lot of customization that we can use, you know, to get this thing more accurate. So that is exactly our goal. How can, because I don't care about any other objects. I only care about mitochondria in this case, right? So why not just fine tune it so it is good at detecting mitochondria and nothing else? Okay, so now we are finally ready to jump into the code, and here it is in Google Colab. I used to do it on my own, using Spider IDE on my desktop, but to make this accessible to everyone, because Google Colab is accessible to everyone for free, I started to do more and more of my videos on Google Colab, so it's easy for you to reproduce, copy my notebook, and all that kind of stuff. Okay, so first thing first, let's look at the runtime and make sure we are using a GPU. Okay, and of course you have to pay for any of these advanced GPUs, but I'm okay with that GPU. And let's go ahead and connect the runtime. I was trying this a few hours ago and it said I reached my daily limit. I'm like, okay, so I hope it connects right now. Looks like it is connecting, but that if you want good access, obviously go ahead and pay. Now I have already connected my notebook to my Google Drive right there. Otherwise, go ahead and mount the drive so you can store your data, you can access your data. That's exactly what I've done. I downloaded these two mitochondria data sets, the data set with images and masks, and I placed it in my drive. So they're accessible. Now they're TIFF stacks, remember? So you cannot just use OpenCV to open this TIFF stack because OpenCV, it reads one image at a time. We'll get to that in a second. I added whatever the presentation I showed you, the text up here. Now, one thing I should mention, here is the link to the dataset. Here is the link to the original code that I shamelessly copied from, but I heavily adapted it to this specific application. This code, original code, actually uses some data set that you need to import using a line of code. It's not like it's difficult to do that. It's just that it may not be relatable to you because oftentimes you have raw data, images and masks. How do you deal with that? That's exactly what I am trying to go through. But again, this is the original code link. If you want, go ahead and look at it. And I did heavily borrow from there. Okay. Now, with that information, let's go ahead and start installing Segment Anything. And this is basically installing it from their Git. So you are going to directly install from their Git. Same with transformers. Now, the implementation that I'm going to use is from, I believe, Hugging Face. Where are we importing these? We'll get to that when we get there, okay? But go ahead and install transformers and go ahead and install the Segment Anything, and also install datasets. And within these datasets, you can actually access the original dataset that this tutorial was referring to. But we'll prepare our data into this datasets format, so go ahead and download that. Now, also in this, one thing I like about how this guy, or I should say this person, I don't know if that's a guy or a girl, but how this person actually did the code, update the default code was by using custom loss functions, right? So go ahead and play with a few different custom loss functions. But anyway, if you want to do that, Mon AI is a good library. So that's why we are installing it. And finally, I am installing Patchify library because we are going to work with large images and we can cut them down into smaller images. One way is you can write your own custom code. Patchify allows you to just write a single line of code to divide large image into regular grid patches. So I'm doing a lot of talking, so let me just go and do some execution of code here. And once this is done, we are going to go to the next step, which is basically importing the appropriate libraries. Of course, NumPy, PyPlot, for plotting, and TIFF file is the library that I use to import these TIFF stacks. You can try scikit-image because scikit-image, to open the TIFF files, it uses the same library in the background. So you can try scikit-image, but I like TIFF file library. So for scientific images, so why not use it? And import OS, Patchify. From Patchify, we're going to import Patchify, obviously only to handle large images where we break it down into smaller ones. And import random. Why? Because later on, we'll just randomly show certain images and display images and masks to make sure it's a sanity check. So that's why random, and ND image for SciPy. So all the libraries you should be familiar with. Okay, even after all that talking, it's still installing, but it's now doing Patchify. So okay, there you go, we're done. Now let's go ahead and import our libraries. There you go. We got all our libraries imported. Now let's load our data into NumPy arrays. Yeah, I'm using tiffile.imread and I'm loading both images and masks. And remember, we have 165 relatively large image, not too large, but large enough to not fit into our memory when we want to do training on a bunch of images using the free resources. Okay, so now we have the large images and large masks. In fact, let's go ahead and add a line of code to see what the shape of these large images is, yeah? So let's go ahead and run this line. And we have 165 images, each image 768 by 1024 in size. Okay, so same with the masks. Now let's go ahead and divide these large images into smaller patches for training, and let's do 256 by 256. So I'm defining patch size as 256, step size is 256. Step size is basically you extract patch size 256 and then move 256 and then move 256. If you do less than 256, that means there is an overlap between patches. Not a bad idea if you know how to deal with the probabilities of objects within the overlapping region. So check a tutorial that I have done in the past on the topic of smooth blending, or smooth blending of predictions. Okay, so now let's go ahead and run this line, and now all I'm doing is for each of these patches, like of images, we have 165 of those, right? For each of those, I'm dividing them into a patch of 256 by 256 with a step size of 256. And I'm repeating that. That's it. And that's for images, and I'm doing exactly the same for masks. So at the end of this, I should have a whole bunch of patches. That's pretty fast. You see? Now let's go ahead and look at the shape of our images, and it's 1980 by 256 by 256. Okay. So our 165 images of 768 by 1024 are now 1980 images of size 256 by 256. Same with the masks. Okay, now you can go ahead and proceed right here, but in my specific example, in these images, a patch may actually have no objects in it, which means it may be all values 0. You may actually run into some error where it says the loss function probably throws an error saying that, hey, you have an empty tensor. I don't know what to do with it. So why use those for training? So this next lines of code is basically, hey, go ahead and see if the pixel value is 0 or in the entire mask. If it is, then go ahead and drop it. If not, I want to use it. So remember, we have 1980 of these images. Now, when you run this, you'll end up with 1642 of those images. Okay, so about 300 images are kind of dropped because they're all dark. I'm dropping both images and masks at the same time. Again, optional step only if you work with this specific data set. Again, I recommend not doing this. Go ahead and run. Start the training and then see what the error looks like, because there is a lot to learn from these errors. Okay, now we are ready to create a data set. Because why do we need to create a data set? Because it serves as an input for our images and masks. And what do we mean by data set? It's basically a dictionary. So we are converting this our images, or adding these images and labels into this data set. So let's go ahead and run it. And once you have it, you can see how the data set, I'm leaving the outputs here from my last test or last run, so you can see exactly what's happening. So my data set, I have, let's go ahead and run it. It's a dictionary where you can see my features are images and labels, and number of rows is 1642 because we have that many images and masks. Now let's make sure our images and masks are loading appropriately, which means I'm retrieving random image and label from my dataset. That's exactly why we need that random library, and then I'm plotting them. So let's run it and then look at the image. So there you go. That's my image, that's my mask. Perfect. This is a sanity check. Let's run this one more time. I spend a lot of time right here because this is what goes into your training, and sometimes if your images are not lined up for whatever reason, you may have done some simple error up here, but this is where you catch it, right? So, okay, now that we're convinced everything is working fine, let's go ahead and extract bounding boxes, because so far what we have an image and a mask like here, but the input that our algorithm actually SAM takes is like a bounding box or a bunch of points or text input, although the text input, I don't think they made that public yet, the API, so we can work with bounding boxes for now, and individual points. No point in getting individual points here. Bounding box is easy to extract from this mask, and how we do that is just go ahead and look at where the ground truth map is not equal to 0 because it's a binary mask, and go ahead and define the bounding boxes right there. So again, this part of the code directly gotten from the original reference that I mentioned, and that's the function. Now let's go ahead and define the class to create a data set, again, that serves as inputs that serves as an input to our masks, images and masks. And let's go ahead and run this. Because when we fetch this get item, it's going to give us images and ground truth masks. Okay, so and the prompt is basically a bounding box, right? So it's actually generating, it's taking my input, it's taking my ground truth mask, and it's also giving me the bounding box around it, because it's invoking this function get bounding box, and it's actually giving us the bounding box. So basically it returns something called input right there, where you have your image and the ground truth mask. That's it. Okay, now initialize the processor. Let's go ahead and initialize the SAM processor. Again, from our transformers library, we have something called SAM processor, and this SAM processor, we are initializing it on our pre-trained. And what model are we using? This VIT based model is what we are trying to use, and this is exactly what we are trying to fine tune in a minute when we load all the weights and continue our training or fine-tuning. Okay, now create an instance of our SAM dataset. So now we have the SAM dataset. Where is it? Where is my SAM dataset? Did I import? Where did I? Yeah, right there. We have the SAM dataset class right there. So let's call it. And from SAM dataset class, we are going to instantiate that using our dataset and our processor. What is the processor again? Our processor is the SAM processor, segment anything model processor. And these are the two inputs that actually goes into this SAM dataset. So let's actually define that for our training. Now you can actually, if you're curious, what the heck is the SAM dataset? Now you can actually look at let's look at the 0th one right there. So you can see 1024 by 1024, the torch size, and the ground truth mask is 256 by 256, and input boxes, we have like 4 coordinates of the input boxes right there, and so on. So this is basically our train data set. And now let's define our data loader. I know I'm just reading the code right there, but these are all one step after the other, right? In a methodical way. We are going from defining your, okay, first let's get the boxes, and then let's create this data set where we can actually get this item that gives us our inputs. And that's exactly what we are doing down here, where it takes the data set and the processor as input, and what processor we are using, the SAM processor right there. Which is nothing but it's taking this pre-trained model. And now let's go ahead and define the data loader. And data loader takes the data set and what batch size, because it's giving us how many number of images, whatever we request right here. Do you want to shuffle it? And I added this drop last because I was looking at, I was encountering this error that I mentioned to you earlier, where it says the tensor. Some weird, I should have noted down what exactly the error was, where completely dark mask gets loaded and it says that something about tensor. I'm like, okay, what's going on? Is it like the last one in the batch that's creating an issue? So I said, okay, drop the last batch or something. Anyway, that's why I added, in case you wonder why I have it. Now let's go ahead and make sure that we are actually getting like each batch. So let's run that, and pixel values, there you go. That 2 represents each batch, right? So in each batch we have 2 images right there. In each batch we have 2 masks right here. So we are all good. And again, if you want to look at the shape, we already have the shape of mask right here. That's exactly what I'm printing down here. No point in running that code. And now we have to load the model. Okay, so my model is SAM model from pre-trained, exactly SAM VIT base is my model. Okay, and anything else? It's going to download it right now. It's 375 megabytes right there. Okay, and for this specific model, we are going to update the loss function that we're going to use, and of course the optimizer is going to be Adam. So we are directly importing it from Torch. And for the loss function, MonAI has a few of these. Dice loss is what we are using, but also try the focal loss or dice focal loss if you're working with multi-class especially. So let's go ahead and run these lines, and now we are all set to train our model. Again, how do we do that? I just set number of epochs equals to 1 because I've already trained it on 10 epochs, but I want you to see how this training is on 1 epoch. And again, our device is CUDA, if it's available. And don't forget, like whenever you do this, I'm pretty sure you know this, if you're familiar with a Torch, you have to push this into whatever device you use. You have to push your data. Where is my sorry, I'm trying to find another line where you kind of push this into. Did I already do that? Just a second. Data loader. Because sometimes here is what's going to happen. You don't push your data set into GPU, but then your model is in GPU, and then it says like, hey, again, it comes with some cryptic error, right? It's not in GPU. So that basically, then you go back and you make sure that, okay, my model is actually available as in the GPU. So that's exactly what we are trying to do. Looking all over. Okay, model to device. This is where we are pushing the model into GPU, and then our data is also available there. And let's go ahead and run these lines. It should tell us exactly how long it takes. And I've done this, like I said, I believe for 10 epochs. Let's see, yeah. 10 epochs, and I saved it, so we are going to load that in a minute, but I want to make sure you see that the training successfully gets started, and it should tell us approximate time right there. Approximate time is shown right here, right there. Okay, so yeah, that's it would take for 10 epochs about probably an hour or so, because for each epoch, well, longer than an hour, each epoch is 12 minutes, so about 2 hours if you're trying to do this for 10 epochs. So let's not do that right now, of course. I have already done that right before recording this tutorial, so let's go ahead and kill this. I saved it, and now you have a trained model on your own data. Now let's go ahead and open it and try to see how it actually does on our data. So first thing first, if you can create this part of the code, you can separate this into inference code. So we are importing SAM model, SAM config, SAM processor from transformers and Torch, and now we are going to load the model configuration. And once you load the model configuration, you kind of also define the processor right there. And then I'm defining my model as my Mito model. What is it? It is nothing but my SAM model, and config is coming from here. Okay, it's just the configuration. Remember, that's not the weights. The weights that we want to use are uploaded from here. Torch.load, and these are the weights. Okay, so let's go ahead and do that. After running this, our Mito model should be ready for segmentation. Now, the next set of lines, while it's doing that, the next set of lines, again, we defined our device as CUDA device, because we have it right here, and I'm pushing my model to that specific device, right? So my Mito model, and you can go ahead and check this. You can read this and see exactly what it's trying to say there. Okay, so now that we have our model ready, let's go ahead and segment our images. How do we do that? Well, all these libraries, you should know that, but first thing first, I'm picking a random image from my trained dataset. First thing first, we are working on the trained dataset, and then I'll show you how to load a completely new image and then do something with it. So first thing first, let's get a random image, a test image, and then ground truth mask. We have a ground truth mask, right? Because this is training data. We have a ground truth mask, but ground truth mask is not the input. The input is going to be a prompt, which is in our case a bounding box. So we are using the function get bounding box, the one that we defined earlier, and we are extracting the bounding box. That is going to be our prompt. And our inputs are going to be our test image, the raw image that we have, and the bounding boxes, right? So the bounding boxes is nothing but our prompt. Remember, you have to give it as a list of lists as input. You'll find that when you run it, it says something, and then you'll figure it out. But anyway, as long as you remember it's list of lists right there, you're good. And and everything else is my Mito model.eval. Again, if you're using Torch, or if you're a Torch person, you know exactly how to instantiate this, and then go ahead and get your outputs by applying my Mito model onto your inputs. And then once you get that, we are applying the sigmoid, because you need to convert that into a probability map, and this is your probability map. Now, to the probability map, we want to set some sort of a threshold because probability is continuous between 0 to 1. You need to set a threshold to binarize your image. And in this case, we are setting the threshold to 0.5. Play with this. This is another important parameter to work with. And bottom part is basically plotting the probability map, the mask, and the image. So let's do this for a few images. Remember, the inputs are image and prompt. Prompt as a bounding box. Okay. Now let's go down here. What is the result? And there you go. You see a mitochondria right here. You see a mitochondria right there. And this is the probability map. That's a pretty good probability map. And there you go, the binarized objects. Let's do this a couple more times and make sure everything looks fine. Yeah, you see around the edges how it thinks there is something right down there. That's why it's very useful if you have smooth blending, where instead of 256 patch with 256 size, step size, if you overlap, like maybe, I don't know, 32 pixel, 64 pixel overlap within that region, now you have continuity because right there, it sees something dark right there and it's like, oh, maybe this is an object. But if you have the rest of the image right here, it has context to interpret how that probability is, right? So then you will minimize a whole bunch of these spurious ones around the edges. Okay, now let's do this one more time and move on to the next image. So there you go. I am pretty happy with this model. Again, I only trained it for 10 epochs, trained it for 100 epochs. This is why I like Detectron, because Detectron is super fast at training, even with small data sets. Okay, now apply a trained model on a large image. Now, how do you apply this onto a large image? We are going to break the large image into patches and we apply it. But you'll see, I think we'll see the problem. Are we gonna, we'll see the problem if we put all the patches together, or I'll leave that to you. Like unpatchify is something that you can actually do if you are putting all the images back together, and see how the segmentation doesn't look that continuous around the boundaries. But I'll leave that exercise to you. But let's, since I only have a large image, this is a different set of images. This is only 12 images that I have, and I am going to load that. Okay, so what's going on here? No such file or directory, 12 training images. So apparently I just wrote the code. I haven't tested this part. So I'm going to pause right now, upload this 12 training Mito images, and I'll continue the video. Sorry about that, guys. Okay, so this part is going to be interesting because I wrote the code, I haven't tested it yet. So let's go ahead and test it live. So yeah, I uploaded my data set of only 12 images, and these are 12 large, meaning 768 by 1024. I'm using Patchify to break them down into 256 by 256. Now, I've written a lot of text here, so go ahead and read that, because now this is unknown image. I don't have ground truth. This is a new image. Now, how do you enter prompts? How do you put bounding boxes around it? I don't know the ground truth. So why not just apply a grid of 10 by 10 or whatever size you want to do it onto the image, just like we have seen it earlier. If I go back to, if I can find my mouse, yeah, you see how we put like everything, a grid of data points. That's exactly we need to generate and go ahead and apply that onto our input image. So that's what this entire thing talks about here, because you can input points right there, which means you have to provide the points in this format, and blah blah blah, whatever. We'll look at the code and we'll understand that a bit better. So our array size is, define the size of the array, 256, right? 256 by 256, and my grid size is 10. I want to do 10 by 10 grid. It's up to you how many ever you want to put. And then I'm generating like the grid of points x and y, and grid of coordinates. So this is our grid of coordinates in our 2-dimension, and convert those into lists. And we need to combine those into a list of lists. Remember, we need to provide this as a list of a list. That's why we are converting that as a list of a list. And then we have our input points as a torch tensor ready to be provided as an input. You just copy the code. You should be all set. I don't think this part is, all of this part is new. This is not from the earlier source I mentioned. This came out of my experimentation on new images. Right, so there you go. So let's go ahead and generate the grid of 10 by 10 points right here. And now let's go ahead and print out the shape, right? I mean, we should have 100 data points, and the shape is 1 by 1 by 100 by 2. Why is it 1 by 1 by 100 by 2? Because you need to have the batch size, number of images you want to process at once. In this case, I'm just providing one image. That is my batch size. And then point batch size, the number of point sets. You can give multiple point sets. Hey, here is my point set number 1, point set number 2. But in our case, we generated one set of points. That's why this is 1 right there. How many points? 100 points. And this last 2 stands for something that that they define here. That's why you see how it says in the documentation, add a 2 right there. That's because we are doing X and Y. For vertical and horizontal coordinates. It's not a 3D grid of data points. That's why we have 2 right there. So our points are in the right shape. Now let's look at our patches. Our patches are in the shape of 3 by 4 by 256 by 256 because I divided my images into my 12 images into this shape. Okay, now let's go ahead and select a random patch for segmentation. And you can select a random patch or pick a specific patch. I mean, this is nothing but selecting a random I and J. But now I'm like, let's just define it 1, 2, because I want to study it by changing things, so I don't want to work with random. Okay, so that is my random patch because I'm extracting. I keep losing my mouse. Okay, the first and second right there. That's what I'm doing right here. And let's go ahead and get that patch. And I'm defining that as my single patch. I'm converting that into a pillow. Again, this image is a pillow object. Yeah. So that's what I'm doing right here. And first try without providing any prompt, no bounding box or inputs. So my input right here is a processor. And remember, the processor takes multiple inputs. Image as an input and the prompt as an input, right? In this case, I'm not giving any prompt. In the next case, we will provide our input points as prompt. But first, let's not give any prompt as input and go ahead and evaluate the image. So the rest of the code is very similar to what we saw earlier, which is you apply a sigmoid, which means you get a probability, and then you apply a threshold to convert that into binary, and we're going to plot it. Okay, a lot of talking. Let's just look at some results now. So there you go. This is exactly what I showed you earlier. You have an image, obviously a mitochondria right here, a mitochondria right here, a mitochondria right here, and the probability should have been higher in these regions for these objects and compared to the background. But I kind of see like some higher probability right here. All of these probabilities is, I believe, less than 0.1 or something. So very low probability. Go ahead and print it out if you want. But now let's go back and provide a, where is it? Where is my, yeah. Let's go ahead and comment this part out. And activate this part, which basically means we are providing our input points, the 10 by 10 grid that we just generated, like 1 by 1 by 100 by 2 right there as my input. And let's go ahead and run. I'm not changing anything else. I'm just providing the prompt right now. That's it. And let's look at the result. This is a much better result, as you can see. Right? I mean, in the top, you see higher probabilities, and this is higher probability for mitochondria down here. And you can obviously play with the threshold to actually get some of these objects. You can actually play with cleaning up these objects, by using morphological filter or any of the other tricks. But I hope you appreciate how amazing this algorithm is. And at the end of this, I again use the term detectron 2 because that is my favorite way of segmenting images compared to any other approach. But segment anything model, if you figure it out how to use it to power up your annotation, for example. So this is where I see segment anything model to be more powerful, because it's faster. It can be used in real time. So you're trying to annotate certain objects. You're like, hey, I annotated 6 objects. Show me all the remaining 500 objects in this image because I want to use this as annotation. For those applications, SAM can be pretty incredible. I really hope you found this tutorial to be useful. And again, as usual, I encourage you to hit the subscribe button. Let's meet in the next video. Bye.